Welcome to the online session conducted by Shriram Dandekar on behalf of Navakokan Education Society's DBJ College, Chiplun. My WhatsApp number and phone number is 94200 You can ask your doubts on this number. We are studying Mathematics and Statistics Part 2. This is for arts and science, but the topic today I am going to start, it is useful for commerce students also. So the topic today is for both science and commerce. So let us begin with that topic, probability distributions. In this lesson we are going to study random variables, types of random variables, probability distribution of random variable, discrete random variable, continuous random variable, probability mass function, probability density function, expected value and variance, cumulative distribution function. And the commerce book chapter contains random variable, which is there in science book, types of random variable, continuous and discrete, which is there in the science book, probability distribution of random variable, discrete random variable, probability mass function, cumulative distribution function, expected value and variance, continuous random variable, probability density function, cumulative distribution function. All these topics are covered in science topic also. So only remaining thing is binomial distribution, Bernoulli trial, mean and variance of binomial distribution and Poisson distribution. These topics are there in science book also, but they are in different lesson, different chapter. So let us begin with this lesson from science book. In 10th standard and 11th standard, you have studied some part of probability, and in that part you have studied random experiment and all possible outcomes of the experiment. The collection of all possible outcomes of experiment is called as sample space of that random experiment. Let us start with this year's study. Let us begin with random variables. We have already studied random experiment and sample spaces corresponding to random experiment. As an example, consider the experiment of tossing two fair coins. The sample space corresponding to experiment contains four elements, namely HH. HH means both the coins show heads. HT, TH, TT. TH means first coin show tails and second coin show heads, and so on. You are familiar with this notation. We have already learned to construct the sample space of any random experiment. However, the interest is not always in the random experiment and its sample space. Because sometimes we want some specific value, or sometimes we are interested in the set of some specific values from the sample space, that is one range. For example, if a fair die is rolled, the score we are always interested in greater than 4 may be the case depending on the situation. We are often not interested in the outcomes of random experiment, but only in some number obtained from the outcome. For example, in case of experiment of tossing two fair coins, our interest may be only in the number of heads when two coins are tossed. Listen here. In this experiment, the sample elements are HH, HT, TH and TT. But we are not interested in what are the elements. We are interested in number of heads. This may be the case. We may be interested in number of tails also. For example, in the first element there are two heads. In second element there is only one head. In third element there is only one head. And in fourth one there is 0 head appears. So if I am interested in only number of heads, then I am interested only in number 2, 1, 1, 0. These numbers are associated with this sample space. So we are going to follow a relation between the numbers and the sample space, which leads to the definition of random variable. In general, it is possible to associate a unique real number to every possible outcome of a random experiment. Just now I have shown you that every element in the sample space is associated with a unique integer 2, 1, 1, 0. The number obtained from an outcome of a random experiment can take different values for different outcomes. This is why such number is a variable. This number is variable and it depends on the element. The value of this variable depends on the outcome of the random experiment. Therefore, it is called as random variable. A random variable is usually denoted by capital letters like capital X, Y, Z, etc. Now, consider the following examples to understand the concept of random variable. The first one, when we throw two dice, there are 36 possible outcomes. But if we are interested in the sum of the numbers on the two dice, then there are only 11 different possible values. Sum of the dice, you know that for this experiment the sample space contains 1 1, 1 2, etc. up to 1 6, then 2 1, 2 2 up to 2 6, and in the end 6 6. There are 36 elements in this sample space. But we are not interested in this 36 sample space, but we are interested only in the sum of the numbers, that is the score. Sometimes we say that sum of the scores. For example, for this first element 1 1, the score is 2. The score for the second element 1 2, the score is 3, and so on. The minimum score is 2, maximum score. Second example, if we toss a coin 10 times, then there are 2 raised to 10, that is 1024 possible outcomes. You know that if a coin is tossed only once, there are only 2 possible outcomes. If the coin is tossed 2 times, then there are 2 square, that is HH, HT, TH, TT, 4 outcomes. When coin is tossed 3 times, you know that there are 2 cube, that is 8 possible outcomes. You have studied in 10th standard H, 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 T, etc. I am not writing all over here, just giving you example. So when we toss a coin 10 times, then there are 1024 possible outcomes. But if we are interested in the number of heads among the 10 tosses of the coin, then there are only 11 different possible values from 0 to 10. There can be 0 heads, there can be 10 heads, all. Only these possible outcomes are there where we are interested out of 1024 possible outcomes of the experiment. Third example, in the experiment of randomly selecting 4 items from a lot of 20 items that contains 6 defective items, the interest is in the number of defective items among the selected 4 items. In this case, there are only 5 different possible outcomes, that is 0 to 4. You know that when 4 items are selected from 20, there are 20C4 different ways. 20C4, that is 20 into 19 into 18 into 17 divided by 4 into 3 into 2 into 1 number of possible outcomes, that is in the sample space these number of elements are there. But we are not interested in these number of elements, we are interested only in the number of defective atoms selected out of these 4. So our interest is now restricted to 0 to 4, only these numbers. 0, the minimum value is 0 and maximum value is 4. In all the above examples, there is a rule to assign a unique value to every possible outcome of the random experiment. Since this number can change from one outcome to another outcome, it is a variable. This is the reason why we are going to call it as a variable. Also, since the number is obtained from outcomes of a random experiment, therefore it is called as random variable. Let us see the definition of random variable. A random variable is a real valued function defined on sample space of a random experiment. In other words, the domain of a random variable is a sample space of random experiment, while its codomain is set of real numbers. Thus, function x from the set of sample space to set of real numbers is called random variable. We often use the abbreviation r.v or we may say rv to denote a random variable. Consider an experiment where 3 seeds are sown in order to find how many of them germinate. Every seed will either germinate or will not germinate. Let us use the letter capital Y for the seed germinating and for the letter N for the seed does not germinate. The sample space of this experiment can be written as S is equal to Y. That means all the 3 seeds are germinated. If one of them is not germinated, then there are 3 cases, 1, 2, 3. If 2 of them are not germinated, only one is germinated, then again there are 3 cases. And if no seed is germinated, then this unique case, no, all the 3 seeds are not germinated. In this case, the sample space is 8. None of these outcomes is a number. We shall try to represent every outcome by a number. Consider number of times the letter Y appears in the possible outcome and let us denote it by capital X. Then we have capital X of YYY is equal to 3. Capital X of YYN equal to capital X of YNY equal to capital X of NYY is equal to 2. Remember that X is number which counts only number of Y's in the sample point. Any element in the sample space called as sample point. So in this sample point only 2 Y's are there, therefore X of NYY is 2. X of NYN only 1 Y is there, so its value is 1, and X of NNN is 0. Thus the variable X has 4 possible values, namely 0, 1, 2 and 3. The set of all possible values of X is called range of X, range of function. Since X is a function, it is a range of X. In this example, the range of X is the set curly bracket 0, 1, 2 and 3. A random variable is usually denoted by capital letter like capital X or Y. A particular value can be taken by random variable is usually denoted by small letter x. Note that small x is always a real number and the set of all possible outcomes corresponding to particular value x of capital X is denoted by the event capital X is equal to X. That is, we say that capital X taking the value small x. For example, in the experiment of 3 seeds, just we have seen, the random variable capital X takes 4 possible values, namely 0, 1, 2, 3. The 4 events are then defined as follows. When x is equal to 0, the event is NNN. When x is equal to 1, the event is YNN, NYN, NNY. When x is equal to 2, the event is YYN, YNY, NYY. And when x is equal to 3, the event contains only one element YYY. Note that the sample space in this experiment is finite and so is the random variable defined on it. A sample space need not always be finite. For example, the experiment of tossing a coin until head is obtained. The sample space for this experiment is H or TH, TTH, TTTH dot TTTTT lastly H. Note that S contains an unending sequence of tosses required to get a head. Here S is countably infinite. There are 2 types of infinity. One is countable infinity and other is uncountable infinity. For example, set of real numbers is uncountable infinity. Set of rational numbers is also set of uncountable infinity. But set of integers, set of natural numbers, set of whole numbers, they are the countably infinite sets. The random variable, in this case capital X, from set of sample space to set of real numbers, denoting the number of tosses required to get ahead, has the range 1, 2, 3 dot 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 up to infinity, which is also countably infinite. There are two types of random variables. The first type is discrete random variable and second type is continuous random variable. Discrete means when it is countable and continuous means it is between the given range and we cannot count by number. Definition of discrete: a random variable is said to be a discrete random variable if the number of its possible values is finite or countably finite. The values of discrete random variable are usually denoted by non-negative integers, that is 0, 1, 2 dot dot dot. Remember that this is usually, not always, because in some examples we may find that x can take the value negative, x can take the value positive, x can take the value 0. Examples of discrete random variables include the number of children in family, number of patients in hospital ward, number of cars sold by dealer, number of stars in the sky, and so on. Just now we have seen 2-3 examples. Everywhere the discrete random variable is everywhere the random variable was discrete. Let us see continuous random variable. A random variable is said to be continuous random variable if the possible values of this random variable form an interval of real numbers. A continuous random variable has uncountably infinite possible values, and these values form an interval of real numbers. Example: heights of trees in forest. Remember that heights of trees, the measurement of height, if we use the smallest possible instrument, then the height can be in mm, the height can be in feet, height can be in meter, height can be in say centimeter, inches. We can write the height of a tree 3.42 meter, but if a fine instrument is used, then height can be 3.421 through 2056. However we want the accuracy, that type of instrument can be used and we can get the accuracy. So height of the forest, heights of the trees in the forest, they form some specific interval. 0 is the least height and maximum can be, till now I don't know what is the Guinness Book of World Record for highest tallest tree in the world. It may be 100 meter, etc. I don't know what is the, but it may be somewhat 100 meter, etc. Nextly, weights of student in a class. For student in a class, the maximum weight can be 100 kg, minimum can be 10 kg. So there is one interval of real numbers where you get two values, one lower bound, one upper bound, and all the values are in between. They can be any accurate thing like this: daily temperature of a city, speed of vehicle. These are all examples of continuous random variable. The value of continuous random variable is obtained by measurement. This is important thing. This value can be measured to any degree of accuracy depending on unit of measurement. This measurement can be represented by a point in an interval of real numbers. The purpose of defining random variables is to study its properties. The most important property of random variable is its probability distribution. Many other properties of random variable are obtained with help of probability distribution. We shall now learn about the probability distribution of random variable. We shall first learn the probability of a discrete random variable and then learn the probability distribution of continuous random variable. Let us see the probability distribution of discrete random variable. Let us consider the experiment of throwing two dice and noting the numbers on the uppermost faces of the two dice. The sample space of this experiment, you know it very well, S is equal to curly bracket, first die showing 1, second die showing 1, first die showing 1, second die showing 2, then 1 3 1 4 up to 6 6. You know that ns is equal to 36, the number of elements in the sample space S. Let capital X denote the sum of the two numbers in any single throw. Then we know that the minimum number is 1 plus 1 2 and maximum number is 6 plus 6 12. So the range of X is the set from 2 to 12, set of integers from 2 to 12, set of possible values of X. Then the event when X is equal to 2 is only 1 1. Event when X is equal to 3, X takes value 3. Only two cases, 1 2 and 2 1. Event when X taking value 4, it is 1 3 2 2 and 3 1 and so on. X is equal to 12, that is event when X taking the value 12 is only singleton set 6 6. Now all the 36 possible outcomes are equally likely if the two dice are fair dice. That is, if each of the 6 faces have the same probability of being uppermost when the die is thrown. As the result, each of the 36 possibilities have the same probability 1 upon 36. This leads to the following result. Probability when X is taking value 2 is probability of singleton 1 1 is 1 by 36. Probability X equal to 3, that is probability of the event containing 1 2 and 2 1 is 2 upon 36. Probability of X is equal to 4, that is probability containing the elements 1 3 2 2 3 1, 3 elements, so probability is 3 upon 36 and so on. Counting all the probabilities in the same way, we get a table. The values of X 2, 3, 4, 5, 6 up to 12 and the respective probabilities. Just now we have seen the probability when X is equal to 2 is 1 upon 36. Probability when X is equal to 3 is 2 upon 36. In this way, when I write all the probabilities, I will get this table. And such a description giving the values of the random variable X along with the corresponding probabilities is called the probability distribution of the random variable X. Probability distribution of the random variable X. When I tabulate this, I get the distribution. The definition, the proper definition is given by the probability distribution of a discrete random variable x is defined by the following system of numbers. Let the possible values of x be denoted by x1, x2, etc. And the corresponding probabilities be denoted by p1, p2, p3, etc. Where pi is equal to probability when x is taking value xi for I equal to 1, 2, 3, etc. Note, a discrete random variable can have finite or infinite number of possible values, but they are countable. Sometimes the probability distribution of a discrete random variable is represented in the form of ordered pairs of the form xipi, that is x1 p1, x2 p2, x3 p3, etc. A common practice is to present the probability distribution of a discrete random variable in a tabular form as shown below, or just now we have seen. This is the probability distribution in tabular form. We can express this same probability distribution in the form 2, 1 by 36, 3, 2 by 36, 4, 3 by 36, and so on. Write it in curly bracket, make a set. Then this can be the probability distribution just like this. We must note one thing, pi is greater or equal to 0 for all values of I. That means since the probability is always between 0 and 1, we should have this pi, probability of the event ei, or probability over here in this table. This should be between 0 and 1, and also the summation of all these probabilities equal to 1. That means p1 plus p2 plus p3 plus ... has to be 1. If we see here, addition of all these probabilities will give us 36 upon 36, that is 1. So sum of probabilities is equal to 1. This is one property, and each of the probability is greater than or equal to 0. Let us see the concept probability mass function, PMF. Sometimes the probability pi of x taking the value xi is a function of xi for every possible value of x. Such function is called as probability mass function, in short PMF. PMF, probability mass function of the discrete random variable x. For example, consider the coin tossing experiment where the random variable x is defined as the number of tosses required to get a head. Let the probability of getting head be t and that of not getting head be 1 minus t. The possible values of x are given by the set of natural numbers 1, 2, 3, etc. Probability x taking value I is equal to 1 minus t raised to I minus 1 for I equal to 1, 2, 3, This is just to express. This result can be verified by noting that if head is obtained for first time on ith toss, then first I minus 1 tosses have resulted in tail. In other words, x equal to I represent the event of having I minus 1 tails followed by the first head on the toss. Now we define the probability mass function of a discrete random variable. Let the possible values of a discrete random variable capital X be denoted by x1, x2, x3 dot 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 with respective probabilities pi, that is probability x is equal to xi for I equal to 1, 2, 3. If there is a function f such that pi equal to px equal to xi is equal to f of xi for all possible values of x, then f is called probability mass function of x. For example, consider the experiment of tossing a coin 4 times and defining the random variable capital X as the number of heads in 4 tosses. The possible values of x are 0, 1, 2, 3 and 4. The probability distribution of x is given by the table. When x equal to 0, the probability is 1 by 16. When x is equal to 1, probability is 1 by 4. X equal to 2, probability is 3 by 8. X is equal to 3, probability 1 by 4, and x is equal to 4, probability 1 by 16. You can check it by writing the event. When x is equal to 0, that means no head, that means T, 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 all the 4 tails. So out of 16, since the coin is tossed 4 times, ns is equal to 2 raised to 4, that is 16. Out of these 16 ways, only one way has x equal to 0, that means no heads. So its probability is 1 upon 16. Now exactly one head, there are 4 choices. T, 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 H, T, T, H, T, T, H, T, T and H, T, T, T. Since 4 choices are there to get only one head, so the probability is 4 upon 16, that is 1 by 4, and so on the remaining. Note that probability x equal to x is equal to 4cx into 1 by 2 raised to 4, where 4cx is the number of ways of getting x heads in 4 tosses, and this is given by 4cx. Nextly, we are going to study cumulative distribution function CDF. For this, I will take you back to the previous problem, the first problem. The probability distribution is with us. If I write here fx, capital Fx, for f2 I will get 1 upon 36. For f3 I am going to add these two, so it is 3 upon 36. For f4 I will add these 3, 1 plus 2 plus 3, it is 6 upon 36. Then add all these 4, so that we get 10 upon 36. Add all these, so it is 15 upon 36, and so on. Lastly, you will get 36 upon 36 equal to 1. This is the cumulative distribution function CDF. The definition of CDF tells us that the cumulative distribution function CDF of a discrete random variable x is denoted by capital F, and it is defined as capital Fx is equal to probability x less than equal to x, that is equal to probability summation of the probabilities up to x is equal to x. We can denote it by summation pi or summation f of xi. F is the probability mass function. Small f is denoted by, is the notation for probability mass function. One example is given over here. X has value 0, 1, 2, 3, 4. Its probability mass function PMF small fx is given by 1 by 16, 1 by 4, 3 by 8, 1 by 4, 1 by 16, etc. And capital Fx probability x less than equal to x. First 1 by 16 as it is. For x is equal to 1, add these two, it is 5 by 16. For x is equal to 2, add these 3 to get this. For x is equal to 3, add these 4 to get the answer 15 by 16. And for x is equal to 4, you should get 16 upon 16, that is 1. Always this last value of capital Fx must be 1. For example, consider the experiment of tossing a coil till head is obtained. The following table shows probability mass function and cumulative distribution function of the random variable x, defined as the number of tosses required for the first head. If the first head is obtained at the first toss only, then x is equal to 1. In that case, fx is equal to half, capital Fx is equal to half. If we get the toss, if we get heads at the second toss, then the probability is half first tail and half second heads, that is TH. This probability is half into half, 1 by 4, and addition of these two is 3 by 4. Probability of getting head at the third toss, that is tails, tails, heads. Then probability of tails is half, probability tails is half, probability of heads is half. Half into half is 1 by 8. This probability is 1 by 8, and capital Fx, that means probability of x less than equal to 3 is addition of all these 3, it is 7 by 8. And in this way you can continue the table. Since x is countably infinite variable, it has no end, and therefore this table will always remain incomplete. Before moving to the problems, please note that on a single sample space like this, there can be many different random variables defined. For example, for this sample space, you can define the sample space as the number of heads, or the random variable as the number of tails, or the random variables as the square of the number of heads, or square of cube of the number of tails minus square of the number of heads, etc. Anything you can write for the random variable as per your rule. The rule is different for different situations. Let us see the first problem over here. Two persons A and B play a game of tossing a coin 3 times. If the result of a coin is head, A gets rupees 2 from B. If the result of a toss is a tail, B gets rupees 1.5 from A. Let X denote the amount gained or lost by A. Show that X is a discrete random variable and show how it can be defined as a function on the sample space of experiment. The solution of this is X is number whose value depend on the outcome of the random experiment. So first of all, we have to write the random experiment. X is random experiment. Since the sample space of experiment has only 8 possible outcomes, X is a discrete random variable. Now sample space X S is HHH, HHT, T, HTH, etc. The values of x in rupees corresponding to these outcomes of the experiment are as follows. X equal to h. Note that according to the condition, if there is head, then A gets rupees 2 from B. For single head, A gets 2 rupees. So here 3 heads, 2 into 3, A gets rupees 6. If there are 2 heads, 1 tails, 3 such conditions are there. So for 2 heads, 1 tail, A gets twice 2 rupees and he lost 1.5 rupees once. So in all 2 into 2 4, 4 minus 1.5, A gets rupees 2.5. Now 1 head and 2 tail, A gets rupees 2 and lost twice 1.5. So 2 minus 3, answer is minus 1. And when all the 3 tails occur, the A lost 1.5 each time, that is he lost in all totally 4.5 rupees. Here negative amount shows a loss of the player A. This example shows that x takes a unique value for each element of the sample space and therefore x is a function on the sample space. Further, possible values of x are 4.5, 1, 2.5 and 6. You should note that these are possible values of x. Here minus 4.5 and minus 1 should be there. In this book it is the printing mistake. Please note that this printing mistake. X takes the value minus 4.5 and minus 1. Now homework for you. Read all these problems, solved problems, and if you cannot understand these solved problems, then you may contact me on my mobile number given in the beginning of this lecture. In the next session, we will start with this expected value variance of random variable. We will see all this part and then we will solve some problems from your exercises. So till then, goodbye. Please stay home, stay safe and solve many problems and ask your doubts on my mobile number. Thank you very much.